Hello everyone, welcome to my YouTube channel. This is Pooja pursuing BE in Sri Venkateshwara College of Engineering. My USN is 1VE23EC092, currently studying in second semester, section Infinity, course name Basic Electronics, course code BBEE203. In this video, we'll be seeing about rectifiers, mainly full wave rectifiers. Introduction to rectifiers. Rectifiers are essential electronic devices that play a crucial role in power conversion and signal processing. They are responsible for converting alternating current AC into direct current DC, which is a fundamental requirement for many electronic circuits and systems. Rectifiers come in various forms, each with its own unique characteristics and applications. This presentation will provide a comprehensive overview of the principles of rectification, the different types of rectifiers, their advantages and disadvantages, and their widespread applications in modern electronics. Principles of rectification. AC waveform. Alternating current AC is a type of electrical current in which the flow of electric charge periodically reverses direction. This waveform is characterized by both positive and negative cycles, making it unsuitable for many electronic applications that require a unidirectional flow of current, known as direct current DC. Rectification process. Rectification is the process of converting AC into DC. This is achieved by using specialized electronic components called rectifiers, which allow current to flow in only one direction, effectively filtering out the negative cycles of the AC waveform and producing a pulsating DC output. DC waveform. The rectified DC waveform is still not a pure, smooth DC signal, as it contains some residual ripple from the pulsating nature of the rectification process. Further filtering and smoothing circuits are often required to obtain a clean, steady DC voltage for various electronic applications. Full wave rectifier. A full wave rectifier uses two diodes, D1 and D2, as it can be seen in the figure, and a transformer T1 with center taped secondary winding. A full wave rectifier is basically a combination of two half wave rectifiers. As we can see in this figure, this is one half wave rectifier and this is another half wave rectifier. Combination of these two makes a full wave rectifier. Looking at the operation of full wave rectifier in this figure, we can see that the input transformer voltage is a positive half cycle. This makes the anode of D1 positive and cathode of the D1 is connected to the center tape secondary winding. So it is connected in a fashion of positive to positive and negative to negative. This makes D1 forward biased, and during forward biased we know that it conducts current, that is, it allows the flow of current through it. So the load current direction will be from the top of the transformer secondary, that is through D1 and through RL, from top to bottom and back to the secondary windings, center tape secondary winding. Whereas D2 is reverse biased, and we know that in reverse bias it does not allow the flow of current through it, so it acts as an open switch, and D1 acts as closed switch. This is the output that we will be getting after the transformer's input voltage is a positive half cycle. Similarly, when the transformer's input voltage is a negative half cycle, the D1 diode is reversed bias. It acts as an open switch, not allowing any flow of current through it. Whereas D2 is forward bias and it acts as closed switch. The flow of the load current is from the bottom of the transformer through D2 and RL, that is from top to bottom and back to the secondary tape center winding. So the final output waveform is a continuous series of positive half cycles of sinusoidal waveform. Basically, it is a combination of two half cycles output waveform. So this is the waveforms of full wave rectifiers. So we can see that there is one full wave over here, and in that the positive half cycle, during the positive half cycle, D1 is forward biased and D2 is reverse biased, and this will be the output that we'll be getting. And during the same full cycle, when we take a negative half cycle of that full cycle, we can see that D2 is forward biased and D1 is reverse biased, and this will be the output, and this output is through D2. Similarly, when we take a whole new waveform, and in that if we consider the positive half cycle, again we'll see that D1 is forward bias and D2 is reverse bias, and this will be the output. Similarly, considering the negative half cycle, D2 is forward bias and D1 is reverse bias. So this is a continuous series of the output waveform that we'll be getting, which will be a combination of the two half cycles, and this is called as pulsating output voltage. Now, looking at the negative full wave rectifier, if the polarity of the diodes is reversed, the output waveform is a series of sinusoidal negative half cycles. Negative full wave rectification, that is what we can see. The center tape of the transformer is normally grounded. So the only difference between the full wave rectifier and a positive full wave rectifier and a negative full wave rectifier is that in the positive full wave rectifier, we can see that there is no grounding in the circuit. But then when it comes to the negative full wave rectifier, the center taped secondary winding is grounded so that the polarity of the diodes are reversed. And so the only way to obtain a negative output from this type of a circuit is to reverse the diode polarity. And this is how we'll be getting an output waveform due to the negative full wave rectifier. Coming to the bridge rectifier, AC input. The AC input is applied to the bridge rectifier, which consists of 4 diodes. So in the other full wave rectifier, we had seen that it had consisted of only 2 diodes, but then a bridge rectifier consists of 4 diodes arranged in a specific configuration. Rectification. The diodes in the bridge rectifier allow current to flow in only one direction, effectively converting the AC input into a pulsating DC output. So the flow of current in this bridge rectifier is only in one direction. DC output. The pulsating DC output from the bridge rectifier can be further filtered and smoothened to obtain a stable, clean DC voltage suitable for various electronic applications. Rectifier. A transformer with a center tape secondary winding is expensive and occupies more space. Due to this reason, a bridge rectifier is frequently used for full wave rectification. Now, looking at the operation of a bridge wave rectifier, during the positive half cycle of input waveform, the diodes D1 and D2 are forward biased. That is, they act as closed switch, whereas D3 and D4 are reverse biased and act as open switch. So the load current direction is from D1 to RL and from RL to D2 and back to the negative terminal of the transformer. Similarly, during the negative half cycle of the input waveform, diodes D3 and D4 are forward biased, that is, they act as closed switch, allowing the current to flow through them, and then D1 and D2 are reversed biased, acting as open switch and not allowing the current to flow through them. So direction of current over here is from D3 to RL, and then from RL to D4, and then back to the negative terminal of the transformer. So this is how a bridge rectifier works. We know that the bridge rectifier has 4 diodes, in which 2 diodes are forward biased and 2 diodes are reversed biased. Advantages and disadvantages of rectifier types. Half wave rectifier. Its advantage is that it's a simple and low cost circuit. Its disadvantage is that it has low efficiency, high ripple factor, and inability to utilize both half cycles of the AC input. The advantage of a full wave rectifier is that it has higher efficiency, low ripple factor, and the ability to utilize both half cycles of the AC input. Disadvantages: more complex circuit configuration and higher component count. Advantages of bridge rectifier is that it is compact and has efficient design, and also has low ripple factor and the ability to utilize both the half cycles of the AC input. is available, whereas the disadvantages are slightly more complex circuit compared to a half-wave rectifier. Applications of rectifiers. Power supplies. Rectifiers are essential components in power supplies, converting AC mains power into the DC voltage required by various electronic devices and circuits. Battery chargers. Rectifiers are used in battery chargers to convert AC power into the appropriate DC voltage for charging batteries in a wide range of applications. Motor control. Rectifiers play a crucial role in motor control applications, converting AC power into the DC voltage required to drive and control electric motors. Welding. Rectifiers are used in welding equipment to convert AC power into the high current DC required for various welding processes such as arc welding and resistance welding. Conclusion and key takeaways. Rectifier fundamentals. Rectifiers are essential electronic devices that convert AC into DC, a process known as rectification, which we have already seen in the beginning of the video. They come in various types, each with its own advantages and disadvantages. Second one is rectifier types. The three main types of rectifiers are half-wave rectifier, full-wave rectifier, and bridge rectifier, each with its own unique characteristics and applications. Applications of rectifiers. Rectifiers have a wide range of applications including power supplies, battery chargers, motor control, and welding, among others, making them indispensable in modern electronics and electronical systems. Choosing the right rectifier. When selecting a rectifier for a particular application, it is important to consider factors such as efficiency, ripple factor, and circuit complexity to ensure the most appropriate solution. And with this, we have come to the end of the video. I hope you find this video informative and useful. Please consider liking the video and subscribing to the channel. Thank you.